So have you wondered how networks work? Okay, let's have a look. We're going to start off with looking at Ethernet because you've probably seen that quite a lot, haven't you? So in school, if you look at the computers that you have, there's probably cables coming out of the back, all different coloured cables. So they are what's known as Ethernet cables. And Ethernet is a series of rules which explains how data is physically moved around a wired network. Right, they're to do with the hardware and how the hardware transmits the data. So what exactly are these Ethernet cables, do you know? Well, if you've looked at them, you've probably seen that actually the Ethernet cable has lots of little cables inside of them, and they're little copper wires twisted amongst each other, and they are used to transmit the data between different computers. Now there's different kinds of Ethernet technology as well, just to confuse things, because as technology progresses, speed increases, doesn't it? So the three different speeds that you should be familiar with are classic, fast, and gigabits. Right, classic is actually pretty slow by today's standards. It runs at 10 million bits per second, 10 Mbps. What about fast? What do you think that might be if I said it was 10 times quicker? Yeah, okay, that's 100 megabits per second. And gigabits, the clue's in the name. Yeah, that's 1 billion bits per second, or sometimes it can be written as 1,000 megabits per second. So they are our three speeds, classic, fast, and gigabits. But there is some exciting technology that's not really commonly used, but it is possible to get speeds of 2.5 gigabits per second, and even 5 and 10 gigabits per second. But those kind of Ethernet devices, at the time of recording this anyway, are not really that commonly used at the moment. So, Ethernet rules. Now, we don't need to know at this stage exactly how Ethernet works, because there's huge books explaining all the rules, but basically, what does it do? So the rules explain how data is split into what's known as frames, and those frames whiz around the network. There's some rules about what happens if there's data collisions. So if you think about it, that network cable, sometimes there can be lots of traffic going along there, and those electrons can collide and data can collide, and Ethernet will automatically manage that. So if that happens, it will know what to do. So Ethernet's about how data is physically formatted and how it's physically transmitted. So how all those zeros and ones are converted into electronic pulses and how they whiz around the network. So that's Ethernet that's commonly used in networks, and in particular local area networks. You've probably seen other kinds of network cable as well, so let's have a look at some of those. So generally there's three key types of cables. So shielded twisted pair. So Ethernet cables are actually an example of shielded twisted pair cables, because little pairs of cables are twisted around each other. And the whole purpose of that twist, don't know if you know, you might have done this in science, is to prevent electronic interference. And the twist, essentially, the interference on one cable can cancel out the interference on the other cable. It's quite clever. It's a bit technical. You don't really need to know all the details for GCSE, but just shielded twisted pair, just be aware of that this is one type of cable. Another which you might have seen if you've got a satellite dish on your house, it's called a coaxial cable, or if you use cable internet, you might see this type of cable. So that's where you have a copper core, which is then insulated. Then there's a metallic shield around that, and then a plastic jacket over that. And this is generally used to transmit radio frequency signals, or it's used for cable internet. And then the last type of cable, which I'm pretty sure you've probably come across, is fibre optic cables. So this is quite new, exciting technology. You might have seen this being installed near where you live, perhaps, because in recent years there's been big efforts to go about replacing old copper cables with fibre optic cables. Why do you think they are replacing copper cables with fibre optic cables? Yeah, exactly. Hopefully you've got it, because signals can travel really, really fast down a fibre optic cable. So instead of electrons going down a cable, a copper cable, you have light signals that travel down a fiber optic cable. And these cables are made from either high quality plastic or glass, which just allows you to bounce a light signal down the cable. Of course, light travels really, really fast. So you probably guessed that fiber optic cables are the way to go in terms of the future of networks and the future of the internet, which is quite exciting really, because then people can benefit from services such as streaming movies, which with older types of connection that wasn't really possible. So you might have heard of something called ADSL. Again, this is not vital for GCSE, but ADSL broadband is a type of technology that works over old telephone lines. And it's fast, but it's not exactly super fast, because the speed is really limited by the type of cable that's used, this old copper type of cable. So hopefully you can describe to me a little bit about Ethernet, and you can also describe some different types of transmission media. So it might be worth just pausing this now and just recapping over that. Okay, what about wireless networks? Right, you might have said about, I've got a Wi-Fi device and I use Wi-Fi to connect to the internet. Wi-Fi itself is not the internet, it's just the name of the connection that connects you to a network. So what exactly is it? Can you describe it? Wi-Fi is just radio waves, right? Waves that travel from an antenna from one device to another. It's just electromagnetic radiation that travels along what we call a frequency. So you might have heard of, say, 2.4 gigahertz Wi-Fi or 5 gigahertz Wi-Fi. It's just a signal that travels along a frequency using electromagnetic radiation. Again, the technical details behind it are phenomenal. So here really we're just touching the surface of it. Now you might be thinking, well hang on, my mobile phone doesn't have an antenna sticking out of it, my laptop computer doesn't have an antenna sticking out of it. Well, that's because sometimes they can be internal and inside the device itself, so you won't necessarily see them. And the antennas can be all sorts of different sizes. Now, of course, there's different types of wireless connection, isn't there? There's Wi-Fi, which is the one that you probably use quite a lot. You might have a Bluetooth connection, say, between your mobile phone and a sports watch, or a mobile phone and some speakers. So Bluetooth is used for really, really short range type networks, sometimes known as a PAN, a personal area network. If you've got a mobile phone, you might be using 3G or 4G or 5G wireless technology to connect to the internet. So 4G and 5G, that's different from Wi-Fi. It uses a different kind of technology to connect devices together. So that's Bluetooth, Wi-Fi, 4G. These are just examples of different types of wireless connection. So we do need to know a little bit more about Bluetooth. So when we're using Bluetooth, I mean, you probably know this. If you're connecting devices together, it goes through a process of what's called pairing. So if I want to connect my phone to the speaker system in my car, for example, I have to select the pair option, and then it will come up on my phone saying, are you sure you want to connect? So that's there for security, really, to make sure that that I definitely want to connect to that device and authorize that device, the devices to connect. So Bluetooth is okay for short-range networks. It doesn't have a huge amount of bandwidth available. So yeah, it's fine for transferring music and relatively small amounts of data in a short amount of time. But it's not really meant for high capacity. That's where we use the likes of Wi-Fi networks which have higher capacity, or 4G or 5G. So what about Wi-Fi? What do we need to know? Well, first off, a little random fact. Sometimes people think the word Wi-Fi means wireless fidelity. It doesn't. It's just one of those urban myths. It doesn't stand for anything at all. If you don't trust me, you can look it up on Wikipedia. But of course, remember, not everything we read on the internet is true. But there we go. So Wi-Fi has a bigger range than Bluetooth, say between 20 meters, 150 meters. It just depends on the technology in use and how many obstacles there are in the way of between one device and another. Because when a wave hits a wall, that wall acts as a bit of a dampener, and that reduces the strength of the signal. And you might have also noticed that with Wi-Fi, the more users that you have on a network, the slower it goes. That's because the available bandwidth is shared between all of the users. So if we had a Wi-Fi network that's got a capacity of, say, 50 megabits per second, and we've got 2 users, what's the total bandwidth that each user gets? Yeah, 25 megabits per second. Although in reality that would only apply if both of the users are active at exactly the same time. It can vary. But you get the idea. The bandwidth is just shared between the number of users that those are active on the network. Of course, modern wireless access points, I don't know if you've seen them around school, they look quite interesting, like UFO dishes on the wall. That's what a modern Wi-Fi wireless access point looks like. You might have a wireless access point at home in the form of your internet router. It's part of that device, and it might be worth just looking at that so you get an idea of what it looks like. It might have antennas sticking out of it, or it might not do. They might be internal. If you've got an antenna, generally you can send out a higher powered signal out of it. So usually the range is better if you've got an antenna, but not always. It just depends on the technology. So with any kind of Wi-Fi network, there should be some form of encryption that's used. Right now, Wi-Fi technology can use many different kinds of encryption, but the two I'm going to mention here, there's one called WEP, which was an earlier one, so-called Wireless Encryption Protocol, which in short is rubbish. And the latest standard that's used, as far as I'm aware at the moment, is called something called WPA2, Wireless Protected Access version 2. You don't need to know these, but you just need to be aware that whenever we're using a wireless connection, anyone can theoretically intercept the signal, so we need to make sure it's encrypted somehow. So 4G, or even 5G, 3G, 4G, 5G, how does that technology work? Well, it's a mobile technology. I'm not going to explain exactly how it works because it's rather confusing, and even I don't know. It's even beyond me. It's like one of those magical things that just works. But what is quite exciting about it is that 5G technology, which is currently being developed, can go at speeds of around 100 megabits per second, which theoretically is even faster than what's achievable with Wi-Fi. But the speeds that 5G can achieve do vary, so it's still a technology that's being developed. I mean, some people are getting speeds of 753 megabits per second out of it. So it's incredible, which means you could download a high definition video in about 3 seconds or something ridiculous. So whether 5G will eventually replace the need to use Wi-Fi, well, we'll have to watch this space. What do you think? Do you think that might happen one day? So what about comparing the two? Which one wins hands down, a wired network or a wireless network? Which one do you think is better and why? Yeah, well, it's going to depend on what we're going to use the network for. So fiber optic cables, as we've already mentioned, are super fast. Okay, and we're talking about faster than 4G and 5G technology here. The capacity of fiber optics is incredible. So the advantages of using fiber optic cables is evidently speed, right? And unlike copper cables, they're not affected by any kind of electronic interference because we're sending light signals. This means that we can transfer data over huge distances. I don't know if you've thought about this, but how do you think data gets from one country to another? actually most of it is transferred using fibre optic cables that go under the sea. I mean, yes, some does go via satellite, but actually the vast majority of it, just a couple of cables between one country and another, does the trick, which is absolutely phenomenal. This just gives you an idea of the capacity of fibre optic cables. And the cables themselves, they can be really, really thin. So generally, if you are replacing copper cables with fibre optic in the street, for example, it's relatively easy to do. Although obviously there's a huge cost of that, which is really the drawback of fibre optic cables is actually, there's quite a high cost of purchasing, and then if you're replacing cables, having to dig up the streets and whatnot, there's quite a big expense involved. But is it worth it? I think you'd probably argue it probably is. So wired connections in general are a lot faster than wireless connections. Right, it's a direct connection between two devices, so yeah, it's going to be quick. What about security? Which one do you think is better when it comes to security? Well, I'd argue a wired network is going to be more secure because it's more difficult to intercept wires. If you want to intercept data going along a cable, you have to physically get to that cable. And if it's a fibre optic cable, it's even more difficult to be able to intercept it as well. But if you're interested in that, then maybe go on YouTube and look that up if you want to. Generally, we have fewer interference problems. So with wireless networks, the wireless signal might not be able to penetrate through a thick solid wall very easily. But if it's a cable, we can just route the cable to wherever we want the signal to go. So of course, because wires wires are really good in that it can offer a greater amount of bandwidth than wireless networks. So because of that, they can support a huge number of different users. And of course, unlike wireless networks, they are less affected by interference. So wired networks generally are suitable for when we've got a huge number of users, and we use them for the main backbone of the internet. Now, of course, the drawback for using wired connections is that, well, if you're setting up a network to begin with, then you've got to install all of those cables. So imagine if you've got a new room at school, and this is being kitted out with a wired network. You've got the cost of installing all of the cables, it takes time to set up, and you don't get that freedom of movement. Whereas if it was a wireless setup, well, you don't have the cost of all the cables, very quick to set up, and you can move around everywhere. So maybe replace all those desks with beanbags. Do you think that would be a good idea? Or would that affect the atmosphere of the classroom and getting work done? I'm not sure about that one. Okay, wireless connections. What's so great about wireless connections? Well, you have freedom of movement, so you don't have any wires to trip over, apart from your power cable, perhaps. So you can't do away with cables completely, but yeah, you might be running on battery, which is fine. You can use any device that you want, as long as it supports Wi-Fi. It's relatively easy to install. You don't have to install so many cables. And as I've already said, there was less cost, isn't there? Because you just need your Wi-Fi access point. So it's pretty quick to set up. But of course, the drawbacks of wireless networks is not as fast as wired connections, particularly if you've got lots and lots of users. If you've just got a few users, yeah, it's going to be absolutely fine. But having said that, there is some really super cool wireless technology. So even in an airport, you might have thousands of people connected to a wireless network and it works fine. But generally speaking, the more users you have, the slower it will go. Of course, there's always possible security issues because anyone can be intercepting those radio waves. And we know that the radio wave interference from other devices, even like a microwave, for example, if you've got your microwave going, cooking your tin of beans and what have you, the electromagnetic signal that will emit can actually reduce the speed of your Wi-Fi network, believe it or not. You might have problems with thick walls and signals not being able to penetrate them. So it swings and roundabouts, really. I mean, if you think about wireless technology like drones, so that can make use of Bluetooth. Obviously, you can't have a cable between yourself and a drone. So whether you use a wired connection or wireless connection just depends on what it is that you want to do, that you want to achieve with your network. I've already briefly mentioned about encryption, but can you remember what encryption is? So it's a process of using an electronic key to scramble data, so that when you're sending data from A to B, if there's anyone in the middle that intercepts that data, they'll still be able to see it, but they just won't be able to understand it because it's all been scrambled with an electronic key. So we just need to keep in mind that if we're using networking technology, it's probably a good idea to use some form of encryption, because you never know who might be spying on your data. So how does data actually get from A to B? Well, we can use something called IP addressing. So IP stands for Internet Protocol. So every device within a network will be allocated an IP address, which is used to identify and locate the device. So if you think about it, when you are addressing an envelope, of course you probably just send text messages these days. Okay, let's say you put in someone's phone number into your mobile device. That phone number is essentially their address. So it's the same with computers. Computers have what's known as an IP address, which is used to address where data goes, or to locate devices in a network. So a device in one network can have the same IP address as a device in a different network, and those two networks might be connected together. But what's important is that every device within a single network has its own IP address. If that happens, it's all going to function absolutely fine. And that IP address can change. It doesn't have to be fixed. It's what we call dynamic. It can theoretically change, because IP addresses can be recycled. So if you threw away your computer and bought another one, for example, that new computer might end up having a different IP address. But that probably isn't a very good example. But it is possible for your IP address to change. I mean, if you have to throw away your computer, then someone else, that IP address that you used could be allocated to someone else. That's probably a better explanation. So we have what's called IPv4 addresses and IPv6 addresses. Any idea why? Well, let's take a look. So an IPv4 address is 32 bits long. And you probably know from looking at bit depth that there is a certain number of possible numbers that we can have. So with IPv4, because it's 32 bits long, if you do 2 to the power of 32, you have a number that's just over 4 billion, which is actually quite a lot, but the world is running out of IP addresses, because actually if you look at the core of the internet and all of the devices that are connected to the core of the internet, that number of devices is growing, and it looks like it's going to surpass that 4 billion mark. So because of that, because we don't want to run out of IP addresses, we use something else. Guess what it is? Yes, an IPv6 address. So this is 128 bits long, which means that we can have literally billions upon billions of devices, right? So we're not going to run out of IP addresses anytime soon. So IPv4, let's look at that again for a moment. So an IPv4 is usually written something like 192.168.0.1. So it's 32 bits long, and of course 32 bits is how many bytes? Can you remember? 32 divided by 8 is 4. So an IPv4 address is 4 bytes long. Now you might think an IPv6 address is 6 bytes long. It's not, it's 16. A little anomaly there, but there we go. And usually with IPv6 we write them using hex instead, just because we can. So, what's an IP address used for? To be able to route data from one device to another, or to locate a device on a network. And hopefully you can now describe an IPv4 address and an IPv6 address. But believe it or not, computers don't just have IP addresses. No. They also have what's called a MAC address. Now these are also used to route data. A MAC address is hard-coded into a device. So when you buy a networking device, it will already have a MAC address and it can't be changed. Now I know some of you might be thinking, well, you can spoof your MAC address, etc., etc., but for the purpose of this course, just think it's fixed, okay? MAC stands for Media Access Control. It's quite a tricky one to remember, so it might be worthwhile writing that down somewhere, Media Access Control. So a MAC address is 48 bits long, and it's usually written in hex. So the example I've got here is 001F, 1F, A6, 107A. If you've got a Windows computer, you can actually load up your command prompt and type in ipconfig, as one word, ipconfig/all, and it will list information about your Wi-Fi, about all of your network adapters, and they will include, and the information will include your MAC address. So we spoke about routers in a previous video, and I mentioned about routers forward data based on IP addresses. But a switch works by forwarding data based on device's MAC address. So I got some statements here, and I wonder if you can tell me if they apply to a MAC address or an IP address. So which one is dynamic, i.e. it can change? Is that a MAC address or an IP address? That's an IP address. Which one is static? That's a MAC address. Which one is 48 bits long? That's also a MAC address. Which one is 4 bytes long or 16 bytes long? That's an IP address, so that refers to a V4 or a V6 address. Which one's hard-coded? That's a MAC address. Which one do you think is set using software? I.e. it can change. Yeah, that's a that's an IP address. Which one's used by routers? That's an IP address. And which one is used by switches? That's a MAC address. Okay. Hope you did a good job of that. Right. Okay, now I'm going to move on and talk a little bit about standards. So computers make use of standards, i.e. rules, or you might have heard of the word protocols. So these are used when developing technology and communicating data between devices. So standards can include, for example, ASCII. Right, ASCII is a standard, so an ASCII is a character set of characters, and so long as everyone is using that same standard, then everyone can use ASCII and devices can communicate. There are standards in terms of different types of programming languages and how data should be formatted. So you've probably heard of HTML, right? So if you want to view a web page, you need software that understands that HTML standard. You might have heard of CSV being a standard way of writing out data. So these standards have been developed over the years, and it's really important that everyone sticks to using these standards, because as long as they apply the rules properly, then everything will work. So if you think about it, there's lots of different manufacturers that make networking devices like Linksys ASUS, TP-Link, etc. So all these manufacturers will refer to standards, and they will implement those standards in their devices so that their devices can talk to other devices that might be made by other manufacturers. So this is essentially why standards are really important. It's to make sure that no matter what, different devices, whoever they're made by, different bits of software, whoever they're made by, are able to communicate and talk to each other. Now, of course, if they didn't implement a particular standard and they came up with a new standard, then nothing else would be able to communicate with it. Or if they didn't implement the standard properly, then errors would occur. So these standards are really, really important. Okay, let's look at some of these in a little bit more detail. So we're talking protocols here. So you need to learn this definition that protocols are the rules that govern communication. Protocols are the rules that govern communication. So you can think of a protocol as being like a language. At the moment I'm talking English, and hopefully you can understand what I'm saying. French could be considered another protocol. But in terms of networking, there's lots of different protocols, and which protocol is used will depend on what it is that you want to do. So if you want to send and receive web pages, you implement HTTP. If you just generally want to transfer data across a network, you use TCP/IP. If you are creating a Wi-Fi device, you would implement something called, well, it is actually Wi-Fi, but sometimes referred to as 802.11. And there's various different substandards of that as well. If you're developing a mobile communications device, you probably want to implement 4G or 5G. So what do these protocols detail? Now, you don't need to know all of this, but some of these points are just interesting to think about. So there might be rules about what type of cable to use, or what frequency to send the data at, or how data should be split up, or what kind of compression to use, or how errors should be detected, or how data should be secured. So hopefully this gives you an idea of what we mean by a protocol, a set of rules that govern communication. So as I've mentioned before, it's important that different people, different manufacturers, different people who develop software, that they all stick to using these standard protocols, and in that way they'll then all able to communicate. I mean, imagine if none of these manufacturers worked together on devising these protocols. Technology would not have improved much at all over the last few decades if everyone was just trying to do their own thing. It's only because people work together in developing these protocols at the speed at which technology improves and increases. That only happens when people work together. So maybe that's something to think about as you progress in this subject. So let's look at some of these protocols. We're almost there. We're going to look at some of these protocols and the network layers, and then that will conclude this little talk. So TCP/IP. So these are two sets of protocols that work together, but they're often just bundled together. It's just called TCP/IP. Transmission Control Protocol, Internet Protocol. So these are protocols that are used to transport data reliably across networks. So they'll automatically take care of problems that happen. So let's have a look. What happens when you send data? So say I'm sending an image, or even might be a web page or something like that. TCP will then take hold of that data, and it will split the data into what we call packets. So if you imagine a jigsaw puzzle that's been completed, and you want to send that to someone else. So what TCP would do is split it all up into its individual puzzle pieces, and we call these packets. And you'll see why it does that a little bit in a little moment. So each packet is given a sequence number. Why do you think that's important? Yeah, so that it can be put back together at the other end, hopefully, in order. And each packet is labelled with the IP address of the sender. And guess what else? Yeah, the IP address of the receiver. So in that way, all these packets can be routed to the correct destination. So the packet itself comprises of a header, so the from address, the from IP address, the to IP address, the sequence number, and it also adds something called a checksum, which is used to detect errors. And these are all in the header part of the packet. Now there is other information that's stored in there as well, but we're just going to keep this really simple to begin with. So the header, that's the header of the packet. Then you have the payload itself, which is like part of the image that we're sending. And then you have the trailer, which just marks where the end of the packet is. So we have the header, the payload, and the trailer. So what happens when those packets are received? So we can use a sequence number to put them back into sequence, because it is possible that the packets are not actually don't actually arrive in order, believe it or not, because those packets can go along different routes on the internet or a network, whatever it might be. So we use a sequence number to put the packets back into order. Now, if any packets haven't arrived, TCP is really clever. It can just re-request the bits that are missing. The same if any have been corrupted, it can just request those that have been corrupted. So this is the beauty of using packets, right? Because if one packet is corrupted, we don't have to re-request the whole entire image. We just have to re-request that packet which got corrupted or lost on the way. So that's why we use packets. So TCP IP can manage packet loss. So if a packet is corrupted or lost, we can just say, hey, send us that packet again, please, and it gets sent again. So as long as there's a network connection, TCP will guarantee error-free delivery of data. That's what's so cool about TCP IP. It's been used for years and years and years. It's so good. Okay, HTTP and HTTPS. These are two that you're probably familiar with. So what do we use HTTP for? Hypertext Transfer Protocol. So this is used by software when we are transferring web data. Right, now of course HTTP data can be passed on to TCP IP, and we'll look at how that works when we look at layers, which is like the last bit that I'll be blabbering on about today. So HTTP is used by web browsers to transfer web data between a web client and a web server. So HTTP is pretty cool. It can be used to send any type of media, so whether it's text, images, or video. So this is a key feature of HTTP. It's connectionless, right? So that means we can send a request and wait for a reply from the server, and after getting a reply, the connection ends. So we can actually just request, say, one image at a time, or one web page at a time. It doesn't maintain any kind of connection between you and the web server. So what does a HTTP request looks like? Well, your computer will request a web page and it will wait for a response. The server will reply with the web page and then the connection is dropped. So it doesn't maintain any kind of connection between the two. The connection only exists for as long as it takes just to get the data. It doesn't like leave the connection open. HTTPS, most websites nowadays, I believe, would use HTTPS. So it's exactly the same as HTTP, but the S stands for, what do you think? Secure, right? And that means that an extra layer of encryption, or a layer of encryption, is added, so that any data that's transferred between you and the web server is encrypted. And it usually does this by using something called SSL, a secure socket layer, or TLS, which is a more modern version, transport layer security. So the S, we say, would either mean secure or SSL, but generally I'd use the word secure. So if you are shopping on the internet or using an online bank when you're a little bit older, we need to make sure that we are using HTTPS. XS so that people can't steal our data. FTP, this is one you might not have come across before. So FTP can be used when we are uploading files to a file server or downloading files from a file server. So I've got an image here of an FTP program. So this lets me log on to a file server using a username and password. And then a bit like Windows Explorer, I can drag and drop files from my computer, from my local computer, to a remote computer. So FTP, as long as I've got a username and password, I'm able to upload, download files, rename them, copy, delete, etc. I can do that on a remote computer. And like HTTP, there's an FTPS version as well, which will secure the connection. So FTP is used to upload and download files, and it does that. It will only do that so long as we've got a valid username and password. Okay, email. We're talking email now. There's 3 protocols associated with email. First one is POP, or POP3 to be more precise, which is Post Office Protocol version 3. So what's POP used for? POP is used to download entire emails and attachments in one go. So we can log on to an email server with a username and password, and POP3 is the protocol that takes care of downloading the email. And that's about it. Nice and easy one, I hope. Now, IMAP is a more up-to-date, modern protocol that we use for internet mail. So IMAP stands for Internet Mail Access Protocol. So IMAP is like POP but much better, because with IMAP we don't have to download all of our email in one go. We can actually leave the email on the mail server and just download, for example, the subject line and who the email is from. And it's only if we decide to open that email, well then the email will download. But even so, the email will stay on the mail server until we choose to delete it. So in this way, you can use several devices to access your email. So if you think about something like Gmail, which you might use or accessing email via a website, that will use an IMAP connection. And it's only when you go to delete the email that the email will be deleted off the email server. So when you use POP, by default, it will just download all of your email in one go to one device, and then that's it. Then you can't access it from other devices. But with IMAP, it will leave a copy on the server, so you can access your email from anywhere. And with IMAP, you can organize all your email into folders, and that's done on the server itself as well. So until you actually delete your email, there will remain a copy of your email on the email server. Okay, almost there. Last one for protocols, SMTP. SMTP, Simple Mail Transfer Protocol. So we use this if we're sending email or forwarding email from one computer to another. So if you are sending an email, as long as you've got the right username and password for your mail server, SMTP will then send that email to your email server. Your email server will then use SMTP to forward that email to the recipient's mail server. And then if your recipient wants to access the email, then they could use either POP3 or IMAP to be able to do that. So what's important to remember about SMTP is it both forwards and sends email. It doesn't just send email, but it forwards email too. Okay, last topic for today. You're doing great. Networks are made up of using different layers of technology. So a layer is a division of network functionality. And I've got an image here of a 4-layer model. I mean, there is a 7-layer model as well, but we just have to get the idea that networks are made up of layers. Application, transport, network, data link. These are our 4 layers. And you can think of these as like Russian dolls. So imagine that we are downloading a web page. So the application we might use for that could be Google Chrome, which exists on the application layer. Then that data gets forwarded to the transport layer, which could then use the TCP protocol. So your HTTP data is put inside of TCP data. That's forwarded to the network layer, which could then use IP to address the data. And then that's forwarded to the data link layer, which would then be the physical protocol that we're using. So it could be Ethernet if we're on a wired network, it could be 4G if we're on a wireless mobile network, or it could be Wi-Fi. So the data travels through these layers and then back up through the layers as it goes to the destination. So the benefit of using different layers is that there's a number of benefits really. I mean, firstly, they're interchangeable. So if we look at the data link layer, for example, if you're downloading a website, the data link layer, it could be Ethernet, it could be Wi-Fi, it could be 4G, it doesn't matter. So these different layers are interchangeable. We can use different types of technology on each layer and it will still work like magic. Now if there's any problems in the network, because we're using different layers, it becomes easier to identify where those problems are. So that's another benefit. And of course, anything that's split up generally becomes easier to manage and develop. So we could develop a new application, maybe a new application for internet chats, for example, and we could just focus on the application itself. We don't need to worry about how data is going to be transported through the network or which physical connection it's going to be used. We can just focus on the actual chat application itself. So I've got a summary of the layers here. So on the application layer, possible protocols that could be used there is HTTP, HTTPS, FTP, POP3, SMTP, or IMAP. There are others. The transport layer is generally TCP, although there is another protocol called UDP, which we don't need to know about for GCSE. Network layer is the IP, and we usually group those two together when we're talking about these two, TCP IP. The data link layer could be Ethernet, it could be wireless, it could be 4G. So hopefully you can tell me what is meant by a network layer. That's a division of functionality, i.e. one part of communication that happens between computers on a network, and a reason for splitting a network into layers, because it simplifies the development of networks. It means different layers can be combined in different ways, i.e. the interchangeableness, which is probably not a word, but never mind. Different layers can be developed by different organizations. So that's it for how networks work.